Hi everyone, hope you're enjoying the workshop. I'm back to tell you about clustering at scale. Clustering is a canonical and important part of the graph mining library. I'm Vahab Mirrokni and I'm going to survey a number of papers listed here. Graph mining at its core is about pattern recognition. And an important pattern in a graph are nodes that are local-like. And that's what we call clusters. Clustering has many applications. For example, in feature engineering, we can use clusters as an input to an upstream machine learning model. We can use clustering as a pre-processing step in other graph-based learning algorithms like GCNs and graph neural networks. We can use them for causal inference and experimental design in minimizing interference, as we discussed as an application story in the first part of the workshop. We can use them to enforce privacy-respecting constraints or anonymity constraints, and also in the context of data efficiency, we can use them in diversified sampling, where we sample data like limitedly from each cluster. Because they're very useful, there are many algorithms also developed for this type of problem, and there are many algorithmic techniques. We have hierarchical clustering algorithms, metric clustering, clustering with constraints like balanced and minimum size clustering, and community detection algorithms. The big challenge in developing all these algorithms is doing it at scale. And there are many algorithmic techniques that we have to employ to be able to implement a scalable version of these algorithms. And that's the main focus of the talk. Before diving into one of the applications, let me tell you that an important aspect of developing the clustering library is to design the right algorithms for the right systems. For some of these examples of clustering, for example, connected components, we have several implementations in different systems, and over time we have learned how to design the right algorithm for the right system. We have an implementation in Empirical, MapReduce distributed hash table service in a synchronous mass intensive passing framework, and so on and so forth. And over time, with these improvements, we can get a more reliable and also much faster algorithm for large data sets. And this is what we cover in the last part of the talk. What I'm going to cover mainly is like high-level algorithmic techniques in this talk. Let's start by hierarchical clustering. The clustering method is called hierarchical if it seeks to compute basically a hierarchy of clusters. There are many sequential algorithms for the hierarchical clustering problem. There are hack, single linkage, average linkage, and there are other parallel clustering algorithms like affinity clustering that I'm going to cover next. Affinity hierarchical clustering is a parallel linkage clustering algorithm that can be implemented very efficiently using MapReduce. It's very simple to describe the core idea of the algorithm. We start with a graph, and then we keep the heaviest edge connected to each graph. Each node is trying to connect to the heaviest edge connected to it. So this forms a set of rooted trees that can be computed in one round of MapReduce with the right use of distributed hash table service, and that can serve as the first level of clusters. Then what we do is like we compute these clusters, and then we compute a graph over these clusters, but aggregating the information across clusters. The aggregate function could be average linkage, single linkage, max linkage, and so on. Then we iterate and recluster. In a recent NeurIPS paper, we show good theoretical properties of this algorithm. We show also good empirical properties. An important note here is that because it's very simple and very scalable, affinity hierarchical clustering is a subroutine in many other clustering applications that we develop. So also different tweaks and different variants of affinity clustering algorithm have been very successful in achieving good performance. In the NeurIPS paper, we also compare the quality of this algorithm to other sequential hierarchical clustering algorithms. Even though the affinity clustering is implemented in parallel, when we compared the quality to the sequential algorithms on these data sets with ground truth, we observed that the quality of the output is even better. And we also compared with algorithms like k-means, and the quality of the algorithm over the ground truth is like similar or better than the k-means implementation as well. We also show that this algorithm can be implemented on graphs with trillions of edges, and shows like big improvements in like speed up in running time compared to other algorithms. Now, let me tell you an application of affinity clustering algorithm in distributed balance partitioning. Distributed balance partitioning problem is a problem in which we are trying to divide or partition the graph into k pieces and minimize the cut, minimize the weight of edges that go across clusters. But we want to do it in a way that the clusters also have like almost equal size. The problem is very hard to solve and NP hard to even approximate. The best approximation algorithms for it are based on linear programming or semi-definite programming, and they are not useful in practice for very large graphs. Our goal is to solve them at scale for graphs with billions of edges, and for that reason, we developed a three-stage heuristic to solve this problem. The first stage of the heuristic is to compute an initial ordering of nodes, and over there we use actually affinity clustering. It's an important part of the algorithm that gives us initial partitioning. Then we use this initial partitioning to also optimize further using semi-local moves or boundary optimization, as you see here. There are different techniques that are applied in post-processing. Let me tell you about the initial ordering, which is an important part of the algorithm. For geographs, we use space-filling curves. But for general graphs, but we don't have such a space-filling curve, we use affinity hierarchical clustering. We basically first make the graph edge-weighted by computing some similarity ranking score, and then we apply affinity, we get a tree, and we use the order of leaves in the tree to get the initial ordering of the algorithm for balance partitioning. We compare the quality of this algorithm to many other previously studied algorithms. For example, for the live journal dataset, we compare it with the spinner and the UV13 algorithm, and we observe that even the affinity ordering algorithm outperforms the previously optimized algorithms. Then we want to partition the graph into 20, 40, to up to 100 partitions. Another interesting thing is that we get basically a fully balanced solution as opposed to basically solution that is like has 5% error in terms of balanceness. When we apply the extra techniques and make it more balanced partition, we get even a better solution with like order of like maybe around 30% improvement over the baselines. We also compare it with these other algorithms, FNL and METIS. METIS is a known algorithm for like single machine, like graph partitioning. We note there that the quality of the solution is still better, and that we get like full balanced partition. But in the case of very small partitions, for example, 2 partition, the quality of the solution is not the champion. So there are like other algorithms out there that work better, but we get basically a better balancedness in the solution. It shows that also the algorithm is like bottom-up clustering, and it works better as the number of partitions increases. This balanced partitioning tool has many applications at Google. In the paper, we reported an application in the Google Map directions where we want to minimize the number of multi-server source destination pairs when we want to serve a map graph. I'm going to talk about the application in Affinity about caching, and in the first section we talked about using this balanced partitioning algorithm in facilitating A/B experiments. For the application of cache-aware load balancing, the core idea is to cache terms that appear in similar queries together in the backend of like the servers. The idea is that if we cache them together, cache terms that are that appear in the same queries together more often, we get better caching properties and less cache misses. And The reason that we need balanced partitioning is that each server also has a capacity constraint on like the amount of traffic it can handle. First, what we did was to basically compute a balanced partitioning on a graph between terms and queries. And we noticed that there is a good correlation between the value of the cut that we compute on the graph that we use, on the partitioning that we use to solve this problem, and the number of cache misses. So this gave us hope that if we deploy this in a real system, it will be impactful. And with further work, we deployed it in the real system, and we noticed that after deploying this, what we call term affinitized replica selection algorithm on top of another dynamic load balancing algorithm, you get in the order of 30% improvement in the flash I/O bandwidth usage in the backend of search. This was very impactful at Google. Next, let me tell you another technique that is very useful. It's the idea of randomized composable corsets. Let's say we have a graph that does not fit on a machine. It would be nice if we can divide the graph into k pieces and then compute a core solution in each piece, in each machine. And then combine these solutions, compute another small instance, and then solve the problem on this instance. This is what we call the idea of randomized composable coreset algorithm. The things that we have to solve in designing a randomized composable coreset algorithm for a problem is to decide how to partition the original graph, how to solve the problem on each machine, and also how to combine the solutions to compute like one final solution. That's what we do for many problems, like diversity maximization, submodular maximization, and clustering problems. Let me tell you about two of those clustering applications. In the context of distributed metric clustering, we are given a set of points, and we want to divide the data into k pieces and minimize either the maximum distance to the center or minimize the average distance or average square distance to the centers. These are k-center, k-means, and k-median problems. These problems are MP hard to solve, and we seek to develop distributed approximation algorithms. The idea we apply is similar to what I described in the composable coreset slide. We divide the data either randomly or using a locally sensitive hashing technique into pieces. We solve the problem, the clustering problem on each piece. We get basically a number of candidate centers, then we combine those, and then we solve the problem on this, the union of those representatives. So that will give us actually a good set of centers for the k-center, k-median problem. If we want to compute the original assignment for the clustering, we have to also do another stage to compute the assignment. This is an algorithm with good theoretical properties, and it can solve even balanced clustering problems. And it also shows good properties in an empirical study that I'm going to report here. We look at different type of word graphs, map graphs with up to 100 million nodes. These problems we can actually solve on one machine as well with a good machine. But then just to see how good are these algorithms are, we divided the data also to hundreds of pieces to up to 1,000 pieces, and we observed how much we lose in the quality of the solution. And we noted that it's like in the order of 50% and not more. And that shows that for the data sets that don't fit on a machine, this is a reasonable algorithm. This was the clustering on the metric space. If you want to talk about specific algorithm on graphs, the coverage maximization is a related problem where we want to find k nodes in the graph that cover the maximum number of neighbors. Or in other words, we want to cover the whole graph by like a small number of centers around the graph. This is very related to the k-center problem if we have basically an edge for each node, for each pairs of nodes. But in general, we can have like a neighborhood definition for each node in the graph, and basically the k coverage becomes a clustering problem. It can also be defined on a bipartite graph where we put the sets on one side, We want to choose a subset of nodes on one side and maximize the number of nodes on the other side of the bipartite graph that are covered by these nodes or are the neighbors of these nodes. There are good, greedy, sequential algorithms for this type of problem, but they are very sequential and they are very hard to implement in distributed or parallel way. The technique that we've developed to solve this problem is a sketching technique and also the course-set technique. What we do is we generate random numbers for the cluster for each item, and then we keep only like a smaller number of edges in the graph that have like random hash value above some threshold, but then we also make sure that we keep at most some number of edges per node. With this technique, we can show that we don't lose an approximation factor in terms of the quality of the solution. And if we apply the course set on top of it, we lose another constant factor approximation. Empirically, we observe that with 1 to 3% of the data, we can get to 96 to 99% of the quality of the solution on the 100% of the data. So this is very effective in solving this type of problems. Let me just add one point. Throughout the talk, we discussed distributed offline or batch clustering algorithms. In reality, we also need dynamic or online clustering algorithms. There have been recent studies and like an algorithm for online hierarchical aggrometric clustering algorithm in which we need to deal with the splits and merges in a dynamic manner in a hierarchical clustering solution. And we also explore basically making these algorithms, these dynamic algorithms, also distributed and also consistent over time. And this is an active area of research for our team. Let me conclude by saying that clustering is one of the most popular tools in the library. The main challenge to solve the problem is scalability, and we use different types of algorithmic techniques. I talked about message passing, locally sensitive hashing, composable course-set technique, but not about random walk. We covered random walk in the previous talk. We didn't talk about overlapping clustering, and that is covered in other talks, but in EgoNet clustering, for example. And the next talk will also cover some other objectives for clustering, which is in the context of community detection. There are further readings that you can read our recent papers. Thank you for your attention.